Kubernetes deployments are built on a single, powerful premise: infinite uptime. You tell the cluster to keep a web server or an API running, and it relentlessly maintains that desired state, restarting pods the millisecond they fail. But not all infrastructure behaves like a continuous web server. Database backups, AI log processing, and data reporting are finite tasks. They have a strict beginning, a processing phase, and an end. Applying the rules of infinite uptime to a finite task creates a severe structural conflict within your cluster. Consider a heavy asynchronous task, like an AI agent compiling its hourly memory logs. If that task encounters a script error and fails, the standard Kubernetes response kicks in. The deployment controller sees the failed pod and attempts to restore the desired state by instantly restarting it. Because the script is broken, the new pod fails. The system duplicates it again, creating a rapid, endless retry loop. This infinite loop forces the node to continuously allocate processing power to spin up new containers, instantly consuming available CPU and memory allocations. As the node maxes out, it starves the actual customer-facing applications sharing that hardware. A single failed background task takes your entire web API offline. Kubernetes solves this problem through two specific controllers: Jobs and CronJobs. These controllers are explicitly designed to handle finite termination. They introduce rigid parameters that limit execution attempts and dictate exactly how a process should conclude. Achieving cluster stability requires abandoning infinite uptime mentalities when orchestrating scheduled infrastructure batch processes. A Kubernetes job controller guarantees that a specific number of pods successfully complete a task and then intentionally terminate. The first major architectural shift from a standard deployment is the restart policy. You cannot set a job to always restart. It must be set to either on failure or never. However, if a container fails to pull an image or hits a persistent code error, setting the policy to on failure alone will still trigger an endless rapid-fire retry cycle. To build a circuit breaker, apply the backoff limit parameter. Set to 4, the job retries the failed pod exactly 4 consecutive times. If the fourth attempt fails, Kubernetes permanently marks the job as failed, completely halting all further pod creation. Sometimes a script doesn't crash, it just freezes mid-execution. To catch pods that hang indefinitely, you implement the active deadline seconds parameter, forcing a termination if the task exceeds a strict time limit. In batch processing, defining exact failure conditions is just as important as defining success conditions. Jobs are not limited to single isolated tasks. They process massive queues, like running parallel analytics on hundreds of data reports. You control this scale using the completions parameter. This dictates the total target number of successful pod executions the cluster needs to achieve. To prevent those executions from crashing your hardware all at once, you pair it with the parallelism parameter. This sets a strict limit on how many pods are allowed to run concurrently at any exact moment. Configure 5 completions with a parallelism of 2, and the system launches exactly 2 pods. It monitors this first pair and waits. Only when they finish does it trigger the next 2. Finally, the solitary 5th task executes, marking the entire job complete. Decoupling the total volume of your workload from the speed of execution allows engineers to process massive queues without spiking memory limits. For tasks that happen routinely, you use the cron job controller. This simply wraps a standard job template inside a time-based scheduler. But chronological scheduling introduces a dangerous operational overlap. What happens if a task takes 5 minutes to complete, but the schedule triggers a new run every 1 minute? By default, a Kubernetes cron job operates with the concurrency policy set to allow. This means the cluster ignores the status of the current task and blindly spawns a new pod every 60 seconds. This default state exhausts resources, forcing the system to process duplicate data. Control this by setting the policy to forbid. Now, if the previous job is running, the scheduler checks the state, completely skipping the newly scheduled trigger. Forbid is strictly necessary for state-critical operations, like database backups, to prevent corruption. Alternatively, setting the policy to replace instructs the cluster to immediately forcefully kill the currently running job and execute the fresh one. You use replace for dynamic analytics, like weather updates or hourly sales, where spending processing power on stale data is useless. Without an explicitly defined concurrency policy, automated schedules will eventually cannibalize themselves. The risks of unmanaged batch processing extend beyond the worker nodes. High-frequency jobs directly threaten the Kubernetes control plane, specifically the etcd data store. Every time a cron job runs, it leaves behind a permanent metadata object detailing its execution history. A cron job running every minute generates over 1,000 metadata files a day. Unmanaged history limits cause massive database bloat. The internal data store bulges under the weight, drastically slowing down API response times across the entire cluster. To maintain stability, configure the successful and failed jobs history limits. These fields trigger automated garbage collection. By keeping only the 3 most recent executions and a single failure record, the cluster actively prunes the database. Application health means nothing if the cluster's core database is crushed by its own logging metadata. All of these logical cluster parameters eventually collide with the physical reality of cloud infrastructure, particularly during disaster recovery. Consider an incident involving a major Australian financial institution. They experienced a complete regional outage that forced their services offline. During the restart phase, the cloud provider's regional zone simply did not have the available compute resources to fulfill the on-demand cluster requests. Despite advanced Kubernetes configurations, the cloud is strictly constrained by finite physical hardware. If you rely on on-demand scaling during a disaster, resource-heavy cron jobs like AI data processing and massive database restorations will fail to schedule because the region lacks the guaranteed hardware capacity. The system architecture rule is clear. Rely on Kubernetes parameters for operational guardrails, but never rely on on-demand scaling for mission-critical batch loads during a disaster. You must secure pre-purchased capacity. Kubernetes configurations dictate the logic of a system, but true resilience requires aligning that logic with physical, pre-planned reality.